So the binomial theorem notes that we did last class only went over how to do full expansions, but we're not always going to be doing full expansions, especially once we get past a certain power. We're only going to be asking you for certain terms in an expansion. And in order to do that, you need to know the formula that Pascal actually used to generate his triangle. So in order to understand what that formula is doing, we're going to be talking about some probability. So back when you guys, way back when you did probability, you learned how to do combinations of things. So what a combination means, it says list the letters A through D, and it says how many ways could you choose two of them. And this part right here, when order doesn't matter, what that means is if you choose A and B, it's the same thing as if you chose B and A. That's what order not mattering means. So if I listed all the ways that I could choose two of the letters from A through D, so for example, I could choose A and B together. I could choose A and C together. I could choose A and D together. But I could also choose B and C together, and B and D together, or I could choose C and D together. Any other combination that you could think of would be repetitive. For example, if I said, oh, I could have chosen C and A, well, that's the same thing as the AC that's already listed in the top row, so we wouldn't include it. Okay? And so what we've got here is we've got a total of 6 ways that we could choose 2 letters out of the first 4 letters of the alphabet, if order doesn't matter. Okay, now what we have just done is we've had 4 things and we chose 2. So you could read it 4, taken 2 at a time. The shorter way is just to say 4, choose 2. And the formula for that requires that you remember that factorial symbol from a couple of our homework problems earlier. So what it means is if I have n items and I want to choose j of them, I'm going to do n factorial up here on the top. I'm going to do j factorial here on the bottom, and then I'm going to have n minus j factorial also there on the bottom. So this right here is my n. I had 4 items. That right there is my j. I chose 2 at a time. So according to the formula, I would do 4 factorial over 2 factorial, and then 4 minus 2 factorial. Okay? Now remember what factorial means. This numerator, let me change colors, this numerator right up here, 4 factorial is the same thing as 4 times 3 times 2 times 1. Now that's not going to be too big, but I'm going to show you a trick to this formula as well. Okay, so I'm not actually going to multiply that out yet. So then I have 2 factorial right here in the denominator. That's just 2 times 1. And then, right there in the denominator, I have 4 minus 2 factorial, which is also 2 factorial. So I have another 2 times 1. Well, the way that this formula is always going to end up setting up is that you're going to have numbers in these fractions that will drastically reduce what you actually have to multiply. So just even with these small numbers, look at this. I have 2 times 1 and 2 times 1. I can just cancel them off. The other thing I have is that here I have a 2 and a 4 that would reduce. And so what that means is that no matter how large these numbers get, I'm going to have this fraction where I can cancel a whole bunch of stuff off before I actually have to multiply. Everything is canceled out of my denominator. All I have left is a 2 and a 3 in the numerator, which sure enough is 6. So we've just confirmed with our formula that we had 6 ways of having 4 items and choosing 2 at a time. Okay, now there's some shortcuts. One of the shortcuts says that if you have n items and you want to choose 0 of them, so you have n items and you want to choose 0 of them. So think about that. Let's say we had those 4 letters, A, B, C, D. If I want to choose none of them, there's only one way to do that, and that is literally to choose none of them. Any other choice I make would involve choosing at least one of them. So there's only one way to choose 0 of them. The same thing is true down here. If I had my 4 letters, there's only one way to choose all of them. So if you have n items, there's only one way to choose all of them, n of them. Because any other choice that you make involves choosing something other than all of them. You could choose 3 of them, or 2 of them, or 1 of them. But there's only one way to choose all of them. Okay? So then, the last 2, right here. Okay, so right here, it says you have n items, you want to choose 1 of them at a time. So we have n items, we want to choose 1 of them. So let's go back to our 4 letters. If I have my 4 letters, I could choose 1 of them by choosing A. I could choose 1 of them by choosing B. I could choose C, or I could choose D. There were 4 ways that I could choose 1 of my 4 letters. So if you have n items and you only want to choose 1 of them at a time, there are n ways to do that. And then this is the strangest one of the bunch. Okay, so we're going to have n items and we want to choose n minus 1 of them. So once again, let's look at our 4 letters. So if we have 4 letters right here and we want to choose 3 of them, because that's n minus 1, I could choose A, B, and C together. I could choose A, B, and D together. I could choose A, C, and D together. I could choose B, C, and D together. So I want you to take a second. Think, are there any other possible ways we could choose 3 of our 4 letters together? Nope, there aren't. And so what that means is that when you have n items and you want to choose n minus 1 of them, there are n ways to do it, because we had 4 letters, we chose 3 of them at a time, and there were 4 ways to do that. So what that means here is that there are a couple of numbers here that we already automatically know in Pascal's triangle. Okay? If we look at everything along this diagonal right here, that meets this last situation. We have 0 items, we want to choose 0 of them. Or we have 1 item, we want to choose 1 of them. That's what makes that diagonal automatically all 1s. This diagonal is this situation. We have a certain number of items and we want to choose none of them. And that's what makes these also all automatically 1. And then these situations right here, these 2, we have a certain number of items we want to choose 1 at a time. So that's this second shortcut row right here. And the number of ways to do that is whatever that top number is. So if we have 2 items and we want to choose 1 at a time, there's 2 ways to do it. If we have 3 items and want to choose 1 at a time, there's 3 ways to do it. And then this last one right here is this final situation, this third row. We have 3 items and we want to choose 2 of them. And so there's 3 ways to go about doing that. So once again, remember, we're just trying to show you how Pascal generated the triangle. You don't need to know this to do a full expansion, because we can just quickly recreate Pascal's triangle like we did last week. Okay, the type of problem you're going to use this for is if I gave you guys the very same expansion problem that we did last week. Okay, if I took that 2y minus 3x to the fourth, and I asked you just for the x squared term. And that's all I asked you for in that expansion. You need to keep in mind how to set this up. So think about how this set up last time. Remember that in the first term, that negative 3x was to the power of 0. In the second term, that negative 3x was to the power of 1. It was in the third term that that negative 3x got squared. So that tells me that I'm going to be looking for this term, just that term, because that's the term that's going to have an x squared in it. In that term, you need to also remember a couple of other things. You need to remember what the 2y was doing. And remember the 2y started out at the high power and stepped down. So we don't want to make a habit of having to actually recreate the first few or several steps of our pattern. I'm just trying to make sure you understand what term it is you're looking for and how you would figure that out. So remember that these two powers out here always have to add up to that number right there. So that's why this was a 3 and a 1 and a 4 and a 0. So in the term we're looking for, if this was a 2, so is that. And then the final thing is now we have to use the formula for the coefficient. So remember that formula for the coefficient in the very abstract expansion. I'm kind of crowded over here, but it said that we were going to take whatever n was, so we're raising to the power of 4, so n is 4. So every term is going to have 4 items at the top of its formula for the coefficient. And then this bottom number down here matched this power. So it started out at 0 and it stepped up, just the way that this power did. So that means this is the term we're looking for. We just want to do 4 choose 2 for the coefficient, 2i squared, and negative 3x squared. And then we would simplify just that one term in our expansion. Okay? Now we just did 4 choose 2. Okay, so hopefully we don't have to set that formula up. We already knew that that had become a 6. And then the 2i, when it gets squared, it would become 4y squared. And then the negative 3x, when it gets squared, it's going to become positive 9x squared. And so the term we would be looking for would be 216 y squared x squared, which was the term we got in that full expansion last time. So that's how we use this formula. This formula is allowing us to calculate the coefficient when we don't want to do a full expansion. Especially once we get up to these powers up here. If I had done a power of 7 or even higher, you do not want to have to do a full expansion just to get one term in that sequence. Okay? So this is going to take some practice. We're done with notes for the unit, so the rest of the unit is practice and quiz. Don't forget you have a series quiz tomorrow. I posted a review online. And come in for tutoring if you need help, or at least make sure you're trying the homework at home so you can ask questions in class. Thanks.